Organometallic reactions, mechanisms, reactivity, and applications. Organometallic chemistry encompasses reactions involving compounds that contain direct metal-carbon bonds. These species play a central role in modern synthetic chemistry, particularly in enabling the formation of carbon-carbon and carbon heteroatom bonds under mild and selective conditions. Transition metal complexes, especially those of palladium, nickel, rhodium, and platinum, are widely employed as catalysts in processes ranging from fine chemical synthesis to large-scale industrial transformations such as hydrogenation, hydroformylation, and cross-coupling reactions. Several fundamental reaction classes define the reactivity patterns of organometallic systems, including oxidative addition, reductive elimination, migratory insertion, ligand substitution, transmetalation, β-Hydride elimination, and sigma bond metathesis. Key fundamental organometallic reactions. Oxidative addition. Oxidative addition reactions attach new ligands to transition metals. In particular, they attach organic ligands and are therefore essential to catalytic applications of transition metal reagents to organic synthesis. Typically, in oxidative addition, a metal center, in a lower oxidation state, inserts into a bond, for example, a carbon halide CX bond, causing the metal's oxidation state to increase by +2. One-electron oxidative addition reactions are also known, where the metal center removes one electron from its d-electron configuration. In each case, there is an overall 2-electron change, accompanied by an increase in coordination number. Several types of mechanisms have been established for oxidative addition reactions: concerted, atom abstraction, electron transfer, radical, and radical chain. Small changes in reaction conditions, for example, the presence of oxygen or light solvent variation, can change the mechanism of an oxidative addition. For example, in the Suzuki-Miyaura coupling reaction, oxidative addition of an aryl halide to a PD0 species generates a PD2 intermediate, which is essential for subsequent bond-forming steps. Reductive elimination. Reductive elimination is the microscopic reverse of oxidative addition. In this step, two ligands bound to a metal center couple to form a new covalent bond, accompanied by a reduction in the metal's oxidation state, typically by -2. Reductive elimination can also happen by the elimination of two ligands from two metals, but the reductive elimination of two ligands from a single metal is particularly important since it frees the organic product at the end of the most homogeneously catalyzed reactions. A key geometric requirement is that the two ligands must occupy cis positions before elimination. In many cases, cis-trans isomerization precedes this step. Factors such as increased electron density, higher oxidation state, and the presence of electron-withdrawing ligands can accelerate reductive elimination. This step is crucial in catalytic cycles because it releases the final organic product. For instance, in Heck and Negishi coupling reactions, reductive elimination forms the desired CC bond and regenerates the active catalyst. Migratory insertion. Many organometallic reactions result in the insertion of an unsaturated ligand into an adjacent metal-ligand bond. Another ligand usually occupies the vacant coordination site, which is created by the insertion. The incoming ligand may be any Lewis base, including the solvent. These intramolecular reactions are sometimes referred to as migratory insertions to distinguish them from the intermolecular attack of a nucleophile on the coordinated ligand. General features of migratory insertion reactions. There is no change in formal oxidative state unless the inserting ligand is an alkylidene or alkylidine ligand. The groups undergoing insertion must be adjacent, cis, to one another in the coordination sphere of the metal. When the inserting ligand is a chiral carbon, the reaction usually proceeds with retention of configuration at the carbon. A classic example is CO insertion into a metal-alkyl bond during hydroformylation, leading to the formation of aldehydes. Ligand substitution. Ligand substitution reactions involve the replacement of one ligand in a coordination complex by another. These reactions are often the initial or rate-determining steps in catalytic cycles. Two limiting mechanisms are observed: associative, A, common in 16-electron complexes, involving formation of a higher coordinate intermediate; dissociative, D, typical for 18-electron complexes, where ligand dissociation precedes coordination of the incoming ligand. For example, substitution reactions in square planar P, T2 complexes proceed via associative pathways, forming a transient 5-coordinate intermediate. The trans effect, where certain ligands accelerate the substitution of ligands trans to themselves, is particularly important in D8 systems. Bond strengths in organometallic complexes are generally weaker than typical covalent bonds in organic molecules. For instance, metal carbonyl bond dissociation energies, 25 to 46 kilocalories per mole, are significantly lower than carbon-carbon single bond or carbon-hydrogen bond. Factors which affect the substitution rate include the incoming nucleophile, the leaving group, the central metal ion, and the ligands trans and cis to the leaving group. Ligand substitutions at 18-electron, coordinatively saturated complexes generally occur at significantly slower rates than the substitution reactions of 16-electron complexes. Ligand substitution on the D10, 18-electron, tetrahedral complex. Nickel tetra carbonyl is a classic example of a dissociative pathway. Besides these reactions, there are some other reactions peculiar to organometallic complexes and metal centers, such as transmetalation, β-Hydride elimination, and sigma bond metathesis. Transmetalation. Transmetalation is a general term that describes the transfer of carbon ligands, such as alkyl, aryl, alkynyl, allyl, etc., from one metal to another. Two general types exist: redox transmetallation, involving changes in oxidation state, and redox neutral transmetallation, common in catalytic cycles. This first form of transmetallation can be considered the simplest and typically occurs between two main group metals, as illustrated by the initial example of mercury and zinc reported by Franklin in 1864. The process can be described as an intermolecular ligand transfer accompanied by the reduction of the transferring metal and the oxidation of the receiving metal. This form of transmetallation has also been referred to as oxidative reductive transmetallation or redox transmetallation. The transfer of an organic group from one metal to another is crucial in coupling reactions, for example, Suzuki or Stille coupling, to prepare reactive species. Transmetallation plays a critical role in several cross-coupling reactions commonly applied throughout organic and polymer chemistry, which differ primarily in the specific transmetallation reaction applied. In general, these methods utilize a transmetallation step in which a main group organometallic reagent transfers an alkyl or aryl group to the transition metal catalyst. In turn, the main group organometallic species applied is also typically generated via transmetallation, usually from an initial organolithium reagent. In the case of zinc and magnesium species, for Negishi and Kumada cross-coupling, respectively, the needed organometallic reagent can be prepared, in some cases, directly from the corresponding organic halide, although the use of organolithium precursors is still the more prevalent approach. Beta-hydride elimination. Beta-hydride elimination is a fundamental reaction mechanism in organometallic chemistry where a metal-alkyl complex decomposes to form a metal-hydride alkene complex. This process is essentially the reverse of alkene insertion, 1,2 migratory insertion. The alkyl group must have at least one hydrogen atom on the beta carbon. The metal center must have an empty orbital, vacant coordination site, to accommodate the hydride and the alkene. Also, the beta hydrogen and the metal center must be in a syn-periplanar arrangement to facilitate the reaction. Transition state. The reaction proceeds through a four-membered cyclic transition state. The oxidation state of the metal remains the same. Beta-Hydride elimination is a common, often undesirable pathway for the decomposition of metal-alkyl complexes, particularly in catalysis. While it can terminate catalytic cycles, it is also a key step in certain catalytic processes, such as alkene isomerization. Sigma bond metathesis. Sigma bond metathesis involves the exchange of a metal ligand sigma bond with another sigma bond, for example, CH or HH, through a concerted four-centered transition state. Unlike oxidative addition, this process does not involve a change in the oxidation state of the metal. This mechanism is commonly observed in early transition metals and lanthanide complexes, for example, scandium 3+, zirconium 4+, which lack accessible redox states. The reaction proceeds via a kite-shaped transition state and is important in CH activation and polymerization catalysis. In conclusion, organometallic reactions provide the mechanistic foundation for a wide range of catalytic transformations in modern chemistry. The interplay between elementary steps such as oxidative addition, migratory insertion, and reductive elimination enables the design of efficient catalytic cycles for bond construction. Understanding these processes